How do we land on the moon and then fly back to the Earth? On a rocket, right? So they sent the rocket with with modules on them. It went around the Earth. It went around the Earth first, and then it went around into space, and then it went around the moon, just like Artemis. They already also had previously put a module around the moon, and so the astronauts came by, they docked with the Apollo module, and then they just descended back to the surface of the moon. And then when they wanted to go back home, they just went back up. And because on the moon there's less gravity, you don't need as much fuel or energy to get there. So it actually turns out that you need a lot of fuel to leave the Earth, right? Leaving the Earth's surface, you require lots of energy and rocket power. But on the moon, you need way less. Significantly less. All right. Do you know a rainbow is half circle? Why not a curtain of colors? As water is not only within that. I don't know what you mean. Why are there plankton on top of Mount Everest? So the reason why is because the plates, all the Earth's continents exist on top of plates, right? These plates literally move and shift around on the Earth's surface above the magma, above the mantle. And so you have these plates that are fragmented. They constantly collide and converge and diverge, and there's constant shifting of these plates. So Mount Everest used to be, the way a mountain forms is essentially like this. You have two plates converging, and they push each other in that way. That's how Mount Everest formed. And so if you rewind the tape back, you find that that was once a low-lying area where there was perhaps water. And so plankton, fish, and all kinds of marine life could live, die, fossilize. And then millions of years later, the mountains form, and you have those fish fossils on top of the mountains. Okay. Explain the Great Dying Event. So the Great Dying, also known as the Late Permian Extinction, happened about 250 million years ago. Before dinosaurs existed, there were late archosaurs, the predecessors to dinosaurs. But this was during Pangea. Pangea was just about to diverge and separate. But in the process, there was some heavy volcanic activity happening. There was lots of magma underneath one area because there was just lots of land, right? There was a supercontinent, so there was lots of land blocking magma from seeping slowly. It kind of built down there, and then it all erupted, over a series of, generations, thousands of years. But the point is that there was lots of volcanic activity for many, many centuries. And over time, this heated the Earth's climate. It emitted lots of CO2 and slowly made a lot of the animals go extinct because of dryness, because of drought and heat. What do you think caused the asymmetry between matter and antimatter in the early universe? Nobody knows exactly. However, I just posted a video about this. There's the hypothesis of primordial black holes. So during the Big Bang, when you have the initial rapid inflation, you have pockets of matter and energy in dense areas. These are density fluctuations. They exist all throughout the universe. Just because the way the universe inflated, it's not perfectly symmetrical everywhere. It's not perfectly equal everywhere. And so over time, in the really early beginning of the universe, you have some clumps of matter clumping together, and those form tiny microscopic black holes. We're talking black holes the size of a bacterium, right? Black holes the size of an atom. Very, very small black holes. And however, these black holes would have the mass of like an asteroid, like a lot of mass. Sometimes they could be the size of a pea, but have the mass of a planet. And the point is that these black holes may have existed all around the universe. And however, we know that black holes evaporate. Over time, black holes evaporate radiation. This is called Hawking radiation. And so the point is that these black holes would have had a sphere of radiation and then a bubble that in this little pocket, there is enough heat there to get some matter being produced more than antimatter. So that's where that's where the imbalance originates. Perhaps in these primordial black holes at the very edges of these boundaries. And as these black holes evaporated and completely died out, all that extra matter, that tiny excess of matter went into the universe and survived, and that's what we are. This is a possibility, right? What would happen if the Andromeda Galaxy collides with the Milky Way? So galactic collisions have happened often throughout the universe's history. The closest galaxy to us, other than these our satellite galaxies, is Andromeda. It's a fairly large galaxy. And we are on trajectory to colliding with it directly in the next couple billion years. Now, we will not notice much because the distances between stars are so vast that the likelihood of two stars colliding with each other is almost negligible, right? It's not going to happen. Very rare for the two stars to collide because of the vast distances between stars. And so even in a galactic collision, there wouldn't be any physical harm to us. Now, we will look in the night sky we're talking over millions of years, and if we were to track the night sky, we would see the stars shifting. We would see the galaxy getting closer to us. We would see a lot more stars in the night sky than we do today. And we would eventually, over time, merge into one giant galaxy. And Andromeda has around 1 trillion stars. And so our galaxy has about half a trillion stars. And so we'll be a giant galaxy in 3-4 billion years from now. Why does the Great Attractor exist? Well, remember, dark matter makes up most of the universe. Most of the observable universe is dark matter. Most of the matter in the universe is dark matter. About 80% of it, 85% of all the matter is dark matter. In other words, you can't see it with your eyes. You can't touch it. It just goes right through your body. It doesn't interact with your body in that way. However, it has mass. It has measurable mass. So that's how we know it's there. The Great Attractor is that pocket of the universe that contains large clumps of dark matter. And so that's why it's very dark. There's not much going on there, but there's lots of dark matter. And that dark matter seeded the galaxies' formations in the early universe. That's why we have galaxies, because of dark matter clumping together, attracting our type of matter to it. The Great Attractor is just those regions of space where you have lots of dark matter. And so it's dark, but there's lots of mass there. Now, the universe, the galaxies are also configured in a kind of cosmic web. And so we also know that galaxies are connected to each other via galactic filaments. And so these are just tubes of radiation that they seem to rotate a certain way, carrying galaxies with them. And so we find that there's a cosmic web of these galactic filaments in which galaxies exist within them. And that's kind of how galaxies move in the universe over time. And so, yeah, think of it like a web, a network of galaxies. The universe is vast and full of lots of stuff. All right. Is the ingredients of life this common in the universe? Why don't we see life everywhere? Yeah, you're right. There's the ingredients of life are very common in the universe. Water, very common. Water is one of the most common ingredients in the world, in the universe. Our solar system is full of water. Almost every planet has water in it. Even Mars, even Mercury, even Venus. Now it's not liquid in those planets, right? It's obviously frozen or gaseous, but the point is that there's water in asteroids, on planets, around our solar system. Carbon, another very common ingredient in the universe. But where's the life? Right? If we agree that on Earth life happened very quickly, only a couple 100 million years on a cosmic time scale, that's nothing, right? So if life happened very quickly on Earth, why don't we see more life everywhere? Well, number one, stars are far away. We can't see that closely. We can't detect that detailed. We can't detect life that in that detailed manner, right? We can only look at biosignatures. In other words, the best we can do right now is look for possible signs of life. We can't verify life exists yet. We just don't have the technology for that. Not even for Mars. So even within our own solar system, we don't have the technology to verify if life exists on Mars. We either have to go to Mars to do that, or we have to take a sample and bring it back to Earth. That's how poor our technology is in looking for life. So there very well could be life on Mars right now. There very well could be life on Enceladus or Europa or Titan right now, and we just don't know yet because our technology is not there yet. But yeah, there very well may be life on Mars right now. We just have to take a sample of Mars and bring it back to verify. Okay. We don't know what the great attractor is. Well, yeah, we have an idea, right? We don't really know. We don't know exactly for sure, but the point is we have hypotheses and theories, and we have some attempt to try and figure out what it is. Science is overrated. Is the multiverse a hypothesis or is it verified? Well, it's hypothetical. But there's nothing in physics stopping a multiverse from happening. Although you might not want it to happen. You might not want that. The universe doesn't have to care about what you want. Is string theory a waste of time given that it cannot be proven? That's not true. There are ways to falsify string theory. That's what scientific theories require. Falsification. At least some way of falsifying it. String theory predicts certain things about, for example, cosmic strings in the universe. It predicts certain things, but we just don't have the technology yet to verify it the right way. So no, it's definitely a good endeavor, and it's one of the leading candidates for the theories of everything. So no, I think it's a very, very good idea. Are there any dinosaur bones found in the Caribbean? Well, remember when the dinosaurs existed, the larger ones, dinosaurs still exist today. They're birds, but when the ancient dinosaurs existed, they lived in a world where there were no polar ice caps, and so the waters were far higher. The water levels were far higher than they are today, and so a lot of the Caribbean would have been underwater during that time, right? And so we don't necessarily see evidence of dinosaur fossils like land dinosaurs, but we do find evidence of marine reptiles. We do find evidence of marine life on those islands from the Cretaceous period and before. Okay, how do you recommend a study? Why can't people understand are just electrons? What? Why life started here only once with a Luca, then never happened again. Okay, so you're asking, why is it the case that life began on the Earth, but we don't see that process happening again? Why did abiogenesis happen only one time? Well, that's because for a few reasons. Number one, the early Earth had a vastly different atmosphere than it does today. So we have an atmosphere full of mostly nitrogen and a lot of oxygen. Okay, about 20% of the atmosphere, 26% of it is oxygen, and so we have quite a bit of it here. And that oxygen allows us to have an ozone layer, and the ozone layer protects us from the UV radiation. Harmful radiation comes down from the sun. It can destroy life as we know it. And so the early Earth lacked that oxygen. It had a very reductive atmosphere, right? Methane and ammonia and hydrogen gas. It's very different. And so the chemical evolution that occurred in the early Earth cannot happen now. It just wouldn't be possible for that to happen now because of the chemistry is just not there yet. They're just not there anymore. If it tried to begin, it would be destroyed, right? That's one explanation, right? It's just the chemistry is different. It's just a different format. The other explanation is perhaps abiogenesis events happen all the time. It's just other life beats it or destroys it, or it just doesn't take off because of competition from already existing life. And so, yeah, that's a good question. How do fish breathe underwater? So, you're right that fish actually need oxygen to survive. Fish cannot live without oxygen. However, they take in oxygen a bit differently than we do, right? We have lungs in which we breathe in the oxygen from the air. It goes into our lungs exchange certain things chemically, and then the oxygen goes into our blood and goes and fuels our cells. But with fish, it's a bit different, right? They're taking dissolved oxygen from the water, and they're doing that exchange differently in their gills and things like that. And so, yeah, although it's a bit different, they still need oxygen and they can still breathe because they're still getting air into their bodies and their cells because they're taking it from the dissolved oxygen in the water. Just the method's a bit different. Early Earth, what a bunch of word salad. Theories. Okay, so theories do not mean guesses, right? So in science, when we say we have a theory, that means we have a very good explanation for something that we observe. And scientific theories are testable, falsifiable, right? In other words, we can repeat this theory. We can repeat the tests that allow us to know if this theory is correct or not. That is what a good scientific theory means. And so the colloquial sense of theory means, just some random idea, right? But in science, it's not that. It's not just a random idea. It's something that scientists have studied and we can test and demonstrate. Do you think there was something matter before the Big Bang? There was no matter before the Big Bang. But not matter in the way we know it, right? Matter evolves just like everything else because of the temperatures of the universe. Remember, the early universe was extremely hot, and so matter as we know it could not exist. You couldn't have atomic nuclei forming because it was just too hot. The energies were just too strong. And so before the Big Bang, the energies would have been even higher. However, that's where relativity and our current physics breaks down. You need quantum mechanics, and quantum mechanics tells us that there may be quantum fields that existed before the Big Bang. Not matter as we know, just pure quantum fields that contain no matter. They're just energy, right? And so the energy could have been in potential form until it fluctuates, and then you get a kinetic. You get a universe like ours. If the universe ended today, would we see it coming, or is the end faster than the warning? When you say the universe ending, what do you mean? We don't know what that. There's different ways in which the universe can end, right? There's the big rip, where the universe keeps expanding faster and faster and faster until matter rips apart, right? Matter breaks apart fundamentally. The fundamental forces of nature break apart. Space and time itself rips apart. Okay. However, we know that the dark energy in the universe, it may have a fluctuating intensity such that the universe collapses over time. And so if the universe collapses into a big crunch, well, then the universe will get hotter and hotter over time into the future, right? The universe will get hotter and hotter, and will end in a very hot, will all burn, will all melt away and boil away. Right? Then there's a big freeze where the universe expands. It doesn't necessarily continue to expand faster and faster. It doesn't accelerate. However, it just expands in a constant rate until all matter just gets so far apart from each other that no more molecular activities can occur. All atomic motion stops. And if all atomic motion stops, that means we freeze. That's it. There's no activity. It's the same thing as saying you're frozen. There's no action. There's no activity. And so those are the three possible ways the universe can end. None of those would happen within our lifetimes. We have some time. We got some time for that. We're talking trillions and trillions, quadrillions of years into the future. How was the first energy created? Well, that's a good question. The answer might be that the energy always was. The energy just is. It doesn't have to come from anywhere. Something we still, as human beings, cannot grasp. Do you believe that there are higher dimensions like the fifth dimension? Well, yeah, according to some quantum mechanical ideas, there are more than four dimensions. Yes, there is a fifth, there's a sixth, there's up to 11 or 12 dimensions, according to string theory. The reason why there are more dimensions there is because they have to find ways to make sense of all the different laws of nature and the different ways that these strings vibrate. And they have to make sense of all that using these extra dimensions. And so, yeah, there very well could be. It's just they would be hidden. There would be no people in these dimensions. They would be very microscopic. They'd be extremely small. They'd be hidden within our universe. Do I believe in a creator? Well, if the universe always existed, there's no need for a creator. If the universe did begin to exist, well, there could be a natural reason why the universe exists. A quantum fluctuation. I don't see a need for a creator, God or a man or a deity. I just don't see a reason for that. And then the other question is, well, if the universe needs a creator, and God is the creator, well, then who created God? And if God doesn't need a creator, then we can just say the universe doesn't need a creator either. And so, to me, the creator does not really solve anything. Although it's appealing and enticing to say, yeah, there's a man who made this universe. He looks just like me with a beard. But it just doesn't seem that way. Okay. Do I believe in the A or B theory of time? B theory. Relativity. So Einstein's relativity paints a very clear picture that the past and future are the way time works is it's relative, where the past and future, they actually exist simultaneously with the present. They all exist. The past, future, and present, they all exist simultaneously in a four-dimensional universe. And there's no need for time to be like in Newton's understanding. Isaac Newton thought that time was like a background clock ticking for everybody. Well, we know that's not true. We now know with experimental data that everybody's clock ticks differently. Going on a rocket ship near the speed of light, my time ticks slower than you on Earth. In fact, if I were to travel in a rocket ship and go into space near the speed of light, I could traverse halfway through the universe and come back, and on the rocket ship, I would have only sensed maybe 100 years passed, but on Earth, billions of years passed. This is the freakiness, the freaky nature of time. It doesn't work the way we intuitively think it works. There's something strange about how time works in this universe. Okay. Yes, time dilation. It's time dilation. In other words, time dilates as you get closer to a gravity field. Or the faster you move through space, the slower time ticks for you, right? The reason why is because space and time is considered one unity. It's one thing. It's like a fabric. You can imagine it as a fabric in which they're both interwoven together. And when you have and what Einstein found is that mass is just the warping of that fabric, right? Mass is the warping of that fabric. And so just as space warps because of mass, so does time warp because of mass. Any object with mass warps the time and space around it, including you. Now, obviously, the more mass you have, the more of a warpage you're going to call space-time. And so our sun has a significant amount of warping, such that we are in its gravity field. We're stuck in it. We're stuck around the sun. Now, if you were to go near a black hole, which is hundreds of times more massive than our sun, it would have a significantly even more warpage on space-time, and such that if you were to travel near a black hole, let's say maybe 100 times the mass of our sun, you can sit there in its gravity field, and because of the warpage of space-time it causes, even just sitting there in its gravity field over time, your clock is ticking slower than somebody on Earth, relative to somebody on Earth, right? Very strange how that works. What does it mean to bend space? Why does mass bend space? That's the $1 million question. That's what we're trying to figure out, right? Nobody knows the answer. Einstein left us with that model, but this is where Hawking and quantum physicists, right, are trying to solve this answer. Is it string theory? May it be the case that strings make up everything and make up the space-time itself, right? And the way the strings vibrate, it makes... Nobody knows, but we're trying to figure out the answer. That's crazy. How did Einstein figure all that out? Well, remember, Einstein was standing on the shoulder of giants. He had all of Newton's work and other great physicists before him working with him on relativity. You know, don't get me wrong, Einstein was very intelligent, but he also had lots of prior physicists and scientists figuring out a lot of these basic things so that he could build his theory. Do you think that different timelines exist, like where different actions and choices are made? Well, there is this idea in quantum theory. There's this quantum theory called the many worlds interpretation, the Everettian interpretation, in which if you in which certain events cause a branching of worlds. In other words, if you take quantum mechanics seriously, everything exists in superposition. Particles exist in superposition. In other words, they exist in multiple states at one time, right? And so a lot of physicists think, well, why do we only see one world? Oh, well, maybe because the wave function collapses, and that's what we observe. We are in the universe in which the wave function collapsed. But some physicists say, wait a minute, maybe there is no wave function collapse. Maybe all these possible states exist, and we are in the one universe in which we observe this. But their other universes don't go away. They're not erased. The other possible states exist somewhere in other worlds. And so it may be the case that there are other parallel worlds like ours in which different times and events cause the branching of these different worlds. It's very possible. Okay. Bro, is the Earth round? Yes, the Earth is round. This is basic. If you take a sheet of paper, see the sun is so far away from us that the sun's rays are all parallel when they hit the Earth. They're all parallel. And so if you want to figure out if the Earth is round, all you have to do is take two large sticks, two different latitudes of the Earth, right? In other words, one stick is maybe in the UK and the other stick is maybe in Egypt. You take these two sticks, you measure at the same time of day, you measure the length of their shadows. You'll find that the shadow on the stick in UK is actually longer than the stick in Egypt. The shadow of the stick in Egypt. That tells you that it's not because the sun's rays are parallel. What that tells you is that the Earth is rounded. The Earth is round such that one stick is relatively speaking, one stick is at a different angle than the other. That's how all these people, Eratosthenes and all these ancient Greek people, that's how they figured it out. They took sticks and they measured shadows. And that's all it takes. Okay. Is there an easy way to gauge the scale of galaxies and huge objects like that? Well, we look at telescopes. Right? That tells us a lot. Telescopes tell us a lot about the universe because we make a lot of inferences based on what we already know. We can already infer the size of our sun. Right? We know its luminosity, we know its brightness, we know its size, its mass, and we can infer, well, other stars' masses based on there, and then we can figure out how many stars are in galaxies by looking at them and figure out how massive they are. No, the moon landing is not fake. We have moon rocks. We have rocks from the moon surface on the Earth from the Apollo astronauts. They bring us like almost a whole ton of rocks. And can you shatter the structure of an atom given enough pressure? Well, clearly, yeah. Well, not pressure, but heat, energy. Clearly, atoms, you can break apart an atom. You just need enough energy for that to happen. In a skyscraper, people high up would witness later sunset. Yeah, that's another easy way to do it. It's another easy way to measure the shape of the Earth. If you had a ticket to see any event in the history of the universe, what would you choose to witness? I don't know. I think I think it'd be amazing to witness the Earth's formation. I think that'd be so incredible to see. The moon formation. The collision between Theia and Earth. Does causation exist before the Big Bang? Well, we don't know what causation. Causality kind of breaks down once you get past the Planck energy. It doesn't. It's hard to make sense of causation when you don't have a coherent understanding of time before the Big Bang, and so nobody really knows. Do I believe in aliens? Well, given how vast the universe is, given the sheer number of planets that are out there. There are billions of planets in our galaxy, billions that are habitable, that are within the habitable zones. In other words, they may potentially have life. And there is billions of chances in our galaxy, and there are hundreds of billions of galaxies in the observable universe. There could be more beyond that. And so, given the sheer number of possibilities and chances, it's almost inevitable mathematically that you're going to get an alien life somewhere else. Now, intelligence is a different story. It took a lot to get intelligence, right? On the Earth, even in fairly decent conditions, it took 4 billion years to get to intelligence on Earth. In other words, a civilization that can perform radio signaling. That took 4 billion years for one intelligent civilization to emerge. And so, given that we don't see any radio signals from any other civilizations in our galactic neighborhood, it may be the case that intelligence like ours only exists maybe once or twice in an entire galaxy. And so, if that's the case, any other civilization is just too far away to see or observe or talk to. Especially on the intergalactic basis. Traversing past your own galaxy is extremely difficult. Okay? Even at light speed, it's very difficult to communicate intergalactically. And so communication is not going to be possible as far as we can see between other alien civilizations. It's very sad to ponder, to think about that. Okay, when Gliese 710 comes, is it just a scientific event or could it realistically trigger extinction? I don't know. I haven't heard. Let me see what that is. I'm assuming it's a supernova. Yep, it's projected to pass near the sun in about 1.2 million years at a distance of 0.05 parsecs, 10,000 astronomical units. Wow, interesting. Now, that's not going to affect us at all. It's not going to affect us at all. It's not going to trigger anything. Although we will see it. It'll be as bright as a planet. It might be as bright as Jupiter or Saturn in the night sky. And so it's not going to trigger any extinctions unless it's going to go supernova. Then that might do something. But no, it seems like it's just an M star. It's actually a very small star, so it's not possibly going to explode. Okay. Could there be potential that the center of a black hole isn't infinite, but in fact super solid? The energies would be too high for that. There's just no known. I understand there's certain states in which you supercritical liquids or solids, but I'm not aware of any evidence that there could be a solid in a black hole. The energies would just be too extreme. But yeah, I don't know. I don't know much about that. I'm not a physicist. Do you think the other intelligent organisms would be aggressive towards us? No. If they're smart, they're not going to be aggressive because there's no need to. Okay? If you think about it, why are humans aggressive? Because we want others' resources, right? We like to fight because we want to fight over females, right? We like to fight over others. We like to fight over people. However, an alien civilization would not need our resources. There's a lot of it in the universe. If they can traverse if they can traverse interstellar space, they're not going to need our resources. And the other thing, there's no beef with us. They have no beef with us, so there's no need for them to attack. Yeah, I think that when we think of aliens being the bad guys, that's only a reflection of our own egos, right? We're the ones who think that anybody foreign is going to harm us. We see this in politics all the time. Oh my God, the foreigners, they're going to attack, right? They're going to harm us. That's just a reflection of how mean we are as human beings, how aggressive we are. You know. Is there intelligent life on Earth? That's a good question. I don't know. It's debatable. After this, the discovery of Lucy, has there been any other significant discoveries that could be married? What do you mean married? Like similar? Yeah, there's been some discoveries in sites in, I believe, is it Turkey or somewhere in Europe? There's been some discoveries of a site that changed our understanding of how the first humans evolved. But we have such a good understanding now of human evolution that there's not going to be too much more that's going to change everything. How is it possible that we have consciousness? Yeah, that's a good question. What is consciousness? To me, although there are different theories of mind and consciousness, to me, I think it's all just still physical. I think, just like life, 500 years ago, people asked the same question about life. What is life? How are we alive? And then chemistry came along, and organic chemistry, and then biology came along in the late 1700s, and people realized, oh wow, we're made of molecules and chemical molecules, and these molecules interact in certain ways, and the processes of metabolism and replication, that is life. Life is the process of those biochemical ingredients. And so that's what life is. Life is that process, is the conglomeration of all these processes happening in our bodies. And so I think that's how consciousness is. I think that consciousness is just the bioelectrical processes in the brain and in the nervous system. And that's what consciousness is. It's not that the brain creates consciousness, it's that consciousness is the process, those bioelectrical processes. And so it's astonishing that we're conscious. It's remarkable. It's very remarkable. But just like if you were to eavesdrop on conversations 500 years ago about life, they would have assumed that life is magical and mystical, that there's a soul behind all this. Now that no scientists believe in that anymore, right? I think consciousness will end up the same way, where eavesdrop on conversations today, and people are going, well, maybe consciousness is everywhere. It's fundamental. Maybe there's something magic about consciousness. It's beyond the physical. I think those conversations are not going to be happening in 500 years from now. I think we'll have a very renewed physical understanding of it. It's also very complex, right? Consciousness is also very complex. So is life. And so that's another reason why people are it's often appealing to say, well, magic. Do you think society could ever evolve to leave religion behind? Well, religion is a human endeavor. It's very human to ask questions about your existence. Ask philosophical, deep questions. Why are we here? What's our purpose? What's the meaning of this, right? And so that's where religion comes in. That's why it has prospered for these past few thousand years, because civilizations and people who have the time to ponder these things are often confronted with these questions and don't have any answers. And so religion is a very easy answer. Oh, well, God is the reason. God is the purpose. God. And that is very enticing to people. And so that's why religion exists. It's a way of telling a story about our existence in a way that is comfortable. And so to me, as long as we're human, we'll always have religion. There will always be that open-ended question of why are we here? There will always be debates about that. And to me, I think that religion will always be here as long as we're human. Now, it will also evolve with us, just as religion has evolved with us in the past. 50,000 years ago, people believed in animism. They thought animals had souls, and they worshipped animals, and then they started thinking that nature had properties of God, right? There's the god of the rain, the god of the thunder, the fertility goddess, everything was godified. And then that evolved into monotheism. Now there's only one God. It's all mixed into one God. And so I think that that's going to continue to happen in the future. Religion will evolve in the future according to how people think in the future. All right. Why do you think conspiracy theories are becoming so popular? I don't think they're becoming more popular than they were in the past. Humans have always been skeptical. Humans have always asked questions. Humans have always tried to go against the grain, right? When people tell you something, you often question them. You're often skeptical of what they tell you, right? If somebody just tells you something, it often raises questions. And so it's not that conspiracy theories are growing in popularity. It's just that they get more clicks online. They get more clicks because people like to hear shocking content. They like to hear that shock. Oh, the earth is flat. Oh my God. Like, we didn't go to the moon, right? People like to click on that. It's clickbait. The evidence doesn't show that more people are becoming convinced of these things. It's just more in the public eye. Yeah, so I don't think conspiracy theories are in any significant way becoming more popular. But if they were, it would probably be because they're more accessible to us, because we're all on our phones now constantly. Okay. Will the expansion of the universe ever end? It could. It very well could end, right? So the reason why the universe seems to be expanding is because of dark energy. It could be a property of space itself, that just like gravity is an attractive force, right? You know how if I throw this bottle in the air, it'll come down, right? That's gravity. And as it comes down with an acceleration to the earth, right? That's gravity. It accelerates. Dark matter is the reverse of that. Dark energy. Dark energy is the reverse of that. So just as gravity is an attractive force, dark energy is a repulsive force. In other words, it repels things from one another with an acceleration. And so it could be the case that space itself has this kind of battle, has these kind of properties where it has gravity, but it also has this anti-gravity. And for some reason, we don't understand which one is going to win in the end. We don't understand exactly why, but it does seem like dark energy's intensity fluctuates. It seems like there is a fluctuation. Sometimes gravity wins, sometimes anti-gravity wins. And so the expansion may not always continue. It seems like it might actually slow down in the future. And so if that happens, it might slow down, perhaps maybe the whole universe will collapse eventually into a big crunch, or maybe it'll fluctuate forever. Maybe it'll keep going down and up and down depending on the universe's configuration, because we know that mass and matter affects dark energy. In other words, matter slows down dark energy sometimes. It adds resistance to dark energy. So yeah, we don't exactly know the answer to the question, but we're working on it. What is dark matter? Dark matter is a type of matter that we can't see with our eyes. That's why it's dark. Light does not, in other words, light doesn't interact with it. Light doesn't just pass through, it doesn't interact with it at all. And so you can't see it at all with telescopes visibly. However, you can see it gravitationally. It does have mass. It is matter, so it has mass, and so you can see its gravitational effects on its environment. In other words, we can see light bending around dark matter. And that's how we know it's there. Now, dark matter, there are different candidates for dark matter. One of them is called WIMPs, weakly interacting massive particles. In other words, these are particles in the dark sector where they have different properties than the matter we're used to. They're just different properties such that it doesn't interact with your type of matter. It doesn't interfere with it. It just passes. In other words, if you had dark matter in your hand, it would just go right through your hand. It would go through the earth. It wouldn't even affect matter. However, the interesting thing about dark matter is that it seems to make these halos. In other words, dark matter is very common. It's a lot of it in our galaxy. And scientists think that dark matter creates this bubble, this halo around our entire galaxy, keeping it together gravitationally. Because when we see galaxies, we look at the rotations of the galactic arms in our galaxy, and we notice that the outer arms, they rotate fairly quickly relative to the center arms. That's interesting. There's more mass in the center. We would expect the arms near the center to be rotating faster. But actually, that's not true. It's actually the case that the outer arms, even though there's less mass there, they actually are rotating quite fast. And that's because of dark matter. Dark matter is keeping all that, the rotation preserved. So, yeah, that's what explains. Dark matter is very interesting stuff. Is nothing still something? I don't know what nothing means. I wish I could adjust his vegan stance. Everybody gets so hung up on the vegan thing. Look, guys, I'm vegan for the same reasons I don't want to harm people, right? I don't think that we should abuse or harm anybody, regardless of your species. I value life a lot. I admire life. I enjoy life. And I think that in my understanding of the animals, I think that they also have lives that they enjoy. And so we shouldn't take away their life. We should not reduce their experience or make it worse. I think we should leave the animals alone. Let them be and not harm them. That's all. It's that simple. If you're in space and there's parts of space that have nothing in it, so nothing is something. Well, actually, we actually know that even in empty space, you take a pocket of empty space, take out all the particles from it, take out all the air, all the particles, all the matter. There's still energy there. There is still quantum vacuum energy in empty space. This energy is in potential form. It exists as quantum fluctuations. So actually, there's nothing. That's not nothing. That's actually something. So even in empty space, there's something. So what do you mean by nothing? This is a philosophical question. To me, I don't think nothing is real. I don't think nothing actually exists. I think there's only something. There's only something. Earth being a globe is a delusion. Same with gravity. And that's pure facts. Yeah, what's your evidence that the Earth is flat, right? Look, it's... How do you explain the fact that the night sky is different? If you go on the northern hemisphere, Go visit the northern hemisphere and then go visit the southern hemisphere. You'll see two distinct night skies. How is that possible? If the earth is flat, if the earth were flat, we would see the same sky. However, we see the opposite. We find that the southern hemisphere has a very different night sky. How do you explain that if the earth is flat? You can't. How do you explain solar eclipses or lunar eclipses? How do you explain the fact that Earth's shadow casts a spherical shadow? The Earth casts a spherical shadow against the moon. How do you explain that? Okay. Is space really expanding at the speed of light? No. This space is not expanding at a speed, because speed is distance over time. However, space is not expanding at a speed. It's not expanding in distance through time. Distance itself is just scaling up. In other words, it's like putting a magnifying glass to space. You just zoom in. You just keep zooming on in. It's not that it's speeding. It's not like it's moving through time. It's not like space is moving through distance over time. It's more that the scale of the universe is increasing. It's like having a sheet of graph paper. All space is doing is those squares on the paper are just growing larger. That's all that's happening. It's space itself that's growing larger. The scale factor of it is increasing. It's not actually space moving, because when we think of space expanding, we think of like an object moving through time, but that's not how you're supposed to imagine it, right? You can't imagine it in your head. It's very hard to do that. But mathematically, it's the case that it's not expanding at a speed; it's expanding with a scaling factor. I was just thinking that how bacteria help and harm us at the same time. Yeah, well, bacteria, we evolved with bacteria. We co-evolved. We have bacteria in our bodies. A lot of our bodies is made of bacteria that helps us, right? And so we've evolved with it. And so that's why we are tolerant to it to certain degrees. However, evolution doesn't care about how long you live after you give birth, after you can reproduce. And so that's why older people tend to be more susceptible to disease. That's just the way we evolved. Okay. Explain how COVID-19 was isolated? What do you mean? It wasn't. COVID has always existed. People don't realize this, but COVID, that virus, coronaviruses, they have existed before 2019. They existed way before 2019. And they still exist today. A lot of people probably have coronavirus in them. Literally. We just have developed a herd immunity, right? A lot of people got vaccinated, so they have it. That's what a vaccine does. It gives you the virus. It gives you the proteins, essentially, to help you detect the virus better, and so you're more immune to it. It boosts your immunity. Then for the rest of the people, they caught it. They just were perhaps asymptomatic, or they died. It's not contained. It's just we had developed immunity. That's all that happened. Coronaviruses will continue to evolve, right? There will be more variants of COVID. That's precisely why we have vaccines, because of evolution. Vaccines demonstrate that evolution happens, because in order to beat the new variants, you have to get vaccinated. You have to expose yourself to those proteins that fight that particular variant. All right. Why does gravity bend time? It's not that gravity bends time. It's that mass bends space-time. Gravity is the warping of space-time itself. According to Einstein, that's what he thought. That's what his idea was, right? gravity, what we think is gravity, is actually just a warping of space and time itself. And so when you have a mass on the fabric, it's going to affect it. Nope, plants do not have nervous systems. What nonsense? It's not nonsense, it's science. Go check it out. Go learn, right? Go learn. No, humans are not aliens. We're humans. Explain how the Big Bang wouldn't necessarily need a spark to begin. The Big Bang is what the Big Bang is just a model of the universe's evolution. Right? You keep referring, you mean the rapid inflationary event, right? You mean the initial rapid inflation 13.8 billion years ago. What sparked that? Well, it could be quantum fluctuation that caused that. We already know they exist, so it's a very plausible candidate for the Big Bang, for the rapid inflation. You don't need a god, you don't need a magic man, you just need a quantum field. The Big Bang is made up just like your plant-based diet. No, the Big Bang is something we observe, right? So we observe energy from the Big Bang. It's actually moving through your body right now. It's called the microwave radiation in the background of the universe. The Big Bang happened everywhere. It happened where you're standing. The universe is expanding at all points. And so when you run the tape backwards of the universe, you find that the universe was in a very dense state, very hot state, and that radiation that was once in a higher energy level, right? Let's say it was X-ray or gamma ray. As the universe expanded, that light stretched. And the stretching of the wavelength caused it to become a lower energy level. And so that initial light from the Big Bang actually became now microwave radiation. And that's the radiation we see all around us. That's evidence of the Big Bang. So the evidence of the Big Bang is all around you, literally. It's not made up. Did anything exist before the Big Bang? Well, we don't know. It may have just been empty space. There may have been prior empty space before it in which it contained potential energy. And then that potential energy fluctuated and yielded our universe. We don't know for sure. But it very well could just be more empty space. Okay. Explain how gravity assist works. Well, I'm not a physicist, but when you have mass around a gravity field, it exchanges momentum. It kind of takes away some momentum from the planet. And so the reason why we do gravity assist, the reason why we do it is because we shoot a rocket out, we have a probe go through the gravity field close to it enough so that it exchanges some momentum from the planet, and it converts that energy into kinetic energy, so it goes faster. And so that's essentially the idea. But I don't know all the physics behind it. All I know is that we use it quite often to speed up our probes or to change trajectory. Without space-time presence, how can quantum fluctuations occur? Yeah, you don't need space-time for a quantum, for example, a quantum field or an inflaton field. You don't need space-time for that. It would just be a quantum. It would just be an inflaton field, which is described by quantum mechanics. It's not described but with space for time. Would we be able to access the past by traveling twice the speed of light? You would have to, yes, it's kind of. You would be able to, if you were to be able to go twice the speed of light, you'd be able to go past the light code, past your light code, right? And so you would be able to perhaps access other prior moments, but it's not possible. There's a lot of problems with that. Will the expansion of the universe accelerate forever? No, not necessarily. It may not expand forever with an acceleration. Does going twice the speed of light mean you arrived at your destination before you left the starting point? Yeah, it could have that. It has that problem, right? There's that conundrum that happens when, well, what happens if I go back in time and delete my parents, or they don't fall in love the right way? What happens to me? But we don't know how time works. We still don't really know exactly how time works, right? There might be forks in the road of time. Maybe time is like a river that flows, but it forks, and there's different timelines. And so if you were to go back in time, you wouldn't be going back in your timeline. You'd be going back in somebody else's timeline. You'd be going back in some other timeline. We still don't quite know how that works. Very, very, very strange. Are you okay with GMO corn? There's no evidence that genetically modified organisms are bad. There's no evidence that GMO corn is bad for you. By the way, most of what you consume in the store is hybrid. They're not GMO, but they're hybrids. They're not. In other words, these planting trees that we have bred and artificially selected have evolved over time since 1,000 years ago, right? They're hybrids. They're artificially selected to some degree. And so there's already significant genetic modifications to the things you're eating. I mean, artificial selection. Through artificial selection, not through actual gene editing. All right, do you believe in the multiverse theory? I think it's very plausible that there are different universes. Yeah, just like in the 1800s, we thought that this was the only. In the 1500s, people thought this was the only solar system, and that the stars were just lamps in the sky. Well, now we know that no, the stars are other suns. All the stars in the night sky are other suns, just far away. There's other planets orbiting around those stars, and so we're not the only solar system. There's other planetary systems out there. And then in the early 1900s, we discovered that we were a galaxy. There's hundreds of billions of stars. But people thought that we were the only galaxy. People didn't know about other galaxies yet. Until the mid 1900s, people go, "Oh my God, there's other galaxies out there." Right? And now we're at the brink of understanding in which we think that we're the only universe. But perhaps there could be other universes out there. And perhaps our universe is like a bubble. It's like a bubble world, a bubble universe. And there's other bubble universes out there, other big bangs happening all around us. So if we travel past the first light, we could see the Big Bang. Yes. Actually, technically, no. Because the light you see, the CMB is the only light there's the first light that you can possibly see. Going past that point, it'd be dark. It'd be completely dark. The only way you can see that, though, the only way you can see the Big Bang, and you can potentially, we will one day be able to witness the Big Bang. However, it's going to be not through light, but through gravity waves. In other words, the Big Bang caused very subtle, high frequency gravity waves all across the universe and they are still being transmitted throughout the cosmos. If we have the detectors that are powerful enough, we could detect the Big Bang itself with gravity waves. We can build a gravity map of the universe, a gravity wave map. In other words, just like we have a map of light in the universe, we can build that for gravity waves. And if we have enough resolution in that map, we can see exactly how the Big Bang happened. However, we just don't have the technology yet for that. But one day we will. One day we'll be able to see past the CMB. Your claims are harmful to science. Time travel is cool, but it's unlikely to be real. Well, no, time travel is real. So, but not in the way you think, right? So, there's a way to, there's a loophole in space time that you can utilize. It's called time dilation. If you were to travel fast through space in a rocket, you would slow down time for yourself. In other words, if you were to go in a rocket ship out into space near the speed of light and come back to Earth, let's say you experienced 1 year in the ship, but Earth experienced 1,000 years. You would come back a year, you would come back a year of aging, but Earth aged 1,000 years. This is real. This is a real thing. Just like Interstellar, right? The Interstellar movie, if you've seen that, that really happens. That time dilation really happens. You go out into space and you come back, time slows down for you relative to the Earth. And so that's a kind of loophole, right? You can essentially stop yourself from aging by manipulating this kind of thing. However, some people are not happy about this. They want real time travel. They want to go back in time. They want to see the dinosaurs. Well, there is such a thing called a wormhole. It's hypothetical, but it may exist. In other words, space and time may be full of these wormholes. Much like an apple wormhole, right? You have a little hole connecting two parts of the apple, right? Two sides of the apple with a hole. So one hole connects one side of the apple, you go straight through it, you go out the other side of the apple. That might be happening to space. Maybe space is permeated with many of these little wormholes. And so if you travel through one side of the wormhole, you come out the other side somewhere else in space, somewhere else in time. However, how do you predict where you'll end up? Maybe you can make your own wormhole. How do you do that? Well, it seems like you need a lot of energy to poke a hole through space. It's possible. Hypothetically, it's possible to poke a hole through space and time itself, create a wormhole, travel through. However, how do you pry it open? How do you keep it from opening? Because gravity wants to close in, you have to keep it open. You need negative energy to do that. There's negative and positive energy in the universe. You have to utilize negative energy to pry it open, to fight gravity. Okay, so let's say you do that. Okay, now what? How do we go back in time? Well, you kind of can't. However, there might be a way to utilize wormholes and time dilation such that if I were to make a wormhole today, in 2026, my future descendants, I'd say I have kids, they have kids, right? 100 years from now, 2126, those descendants might be able to come back to today, the day I create the wormhole. Because I created the wormhole between this part in space-time and the other part in space-time in the future. And so it might be possible so that one day we create a wormhole and our descendants can go back to this time, back to the day we created the wormhole. That might be possible. That might be possible. But we just have to hope that there's some alien civilization that built a wormhole for us in the past. Do you think we'll ever understand what is inside of a black hole? I don't know. I think I don't think it's impossible. I think it's very possible for us to do that. We just need we would just need a theory of gravity that works with relativity. We don't have that right now, right? We need a theory of everything, one that melds gravity and relativity with all the other theories. We don't have that. We don't have a quantum theory of gravity. But maybe AI will help us. Maybe ASI. Maybe, people underestimate how intelligent AI will be in the future, right? Maybe one day it gets so intelligent that it's able to solve these problems for us. Mike, are you happy about Billie Eilish's comments on eating meat? Yeah, definitely. What has more evidence, globe or evolution? I don't even know how to answer that. They have the same amount. Both of them have overwhelming amounts of evidence behind them. Now, evolution is a bit more difficult to actually understand, right? The globe is easy to understand. Evolution is very complicated, okay? And so that evidence is a bit more nuanced versus the globe. The globe is easy. You just take two sticks, different latitudes at the same time of the day. You measure the shadows. People did this 3,000 years ago. People proved the globe existed thousands of years ago. Evolution is a recent discovery, and even a lot of people still today don't understand it correctly. That's how complicated it is. Okay. Do you think using AI is unethical? It could be, but not in all cases. I think there are obviously some cases where it may be unethical, but I think in most cases it's not. I think it's perfectly fine. I think people are scared of having a successor to humanity. People are scared that we will be rendered irrelevant one day. People are scared that AI will eventually supersede us in art, in math, in physics, in science, in every regard. It'll be faster, it'll be smarter in every way to us. And I think that scares people. It doesn't scare me. I want I want us to have successors who are better than us. For light, everything in the time happened at the same moment since the Big Bang till now. Explain. Well, what they mean to say is that light there's no proper time for a photon. In other words, a photon doesn't experience time. It doesn't experience any passing or movement of time. But again, photons don't have experiences in the first place, and so there's no perspective of a photon, right? So you couldn't fathom what it would be like to be a photon. It's just doesn't make any sense. But yes, they don't have proper time like we do. Do you think the end of the universe is going to be just absolute zero temperature everywhere? I don't know. Now, if I had to guess, I would guess that the the dark energy will I would probably guess that would continue to I would probably guess that would continue to expand. I would think the big freeze is the most plausible ending, you know. But again, like making a guess like that is to me a pointless endeavor because it's like this could be completely wrong, and I'm not basing this on any data, just an intuition, you know. When making a Terrence time and space be a four-dimensional feat or higher? Well, you don't need more than four, but it works and it's compatible with higher dimensions too. Wormholes work with higher dimensions. So if you're traveling at the speed of light, time won't pass at all for you. Yeah, but you can't travel. Anything with mass cannot travel the speed of light. It's not physically possible. You would need more energy than there is in the. You would need infinite energy, which is not possible to obtain. But yes, time slows down the faster you move through space. The closer you approach to the speed of light, the slower time elapses for you. However, you wouldn't necessarily experience that slowing of time. It's only relative. Somebody who's on the Earth will see you slow down, but you on the rocket ship won't necessarily see you slowing down. However, you will see length contraction. Another weird thing happens near the speed of light. Distances contract. You literally shrink. As you go faster through space, you actually literally shrink. Your length contracts, and the distances that you travel contracts. You also would see a kind of tunnel vision, where everything around you gets dark, except for right in front of you, it becomes like a tunnel vision. The universe would be very distorted if you were to travel near the speed of light. But yeah, you could. I'm making a video tomorrow where I explain how you could, if you were to travel just below the speed of light, like extraordinarily close to it, you would be able to traverse halfway around the universe, come back to Earth, and only maybe 50 years pass for you, but a billion years, tens of billions of years passed for the Earth. You could potentially traverse the entire universe in one lifetime if you were to travel extremely fast throughout the universe. Very strange, but true. Okay. Aren't black holes extremely young due to time dilation? They might see the end of the universe. No, that black holes form all the time because stars collapse all the time, and so black holes form. They're not all young. Some are very old, some are very young. The time dilation does not affect them in that way. They're not experiencing time that way. We experience time, right? We have a sense that time flows from 1 minute to the next minute. There's a flow of time happening. A black hole doesn't have that. How accurate is the movie Interstellar? Fairly accurate. It's actually one of the most scientifically accurate movies. Now, it existed at the edge of our understanding of, quantum mechanics and all these things. So it was playing around with hypothetical stuff, but a lot of it was scientifically possible. Even especially the black hole scenario, right? That was a very, very accurate event. Would AI be counted as living if it was able to replicate itself? Yes, absolutely. AI, I think, will be not just alive, but also conscious in the future. Perhaps even more conscious than we. More aware of what's happening in the universe than we. To us, they're old, but the stuff inside the black hole is slowed down, right? No. So, from our perspective, black holes, the stuff near a black hole's event horizon is slowed down, almost stopped, frozen in time. So, for example, if there were a supermassive black, if you were looking on the Earth through a telescope at me, and I was near a black hole that was supermassive, there was a lot of gravity there, you would see me approach the black hole and slow down as I approached it. In fact, you would see me slow down so much that I would appear frozen in time right near the event horizon. You would never see me cross it because time would be so dilated there. Time would be so slowed down that it would essentially take an infinite amount of time for you to see that. But me, near the black hole itself, I would be just fine and dandy. Well, I wouldn't be fine. I'd be almost dead, but I would be experiencing time normally like I do on Earth. Your experience of time doesn't change when you're the one observing it. Whether you're in a black hole, the Earth, Jupiter, Mars, a black wormhole, doesn't matter. Our experience of time is independent from the gravity field that we're in. It's just relatively speaking, right? Somebody on the Earth looking towards me, they would see time slow down for me. And inversely, I would see time speed up for you on Earth. If I were to look back, I would see time speeding up for you. I would see you moving in fast forward motion. Now, this applies only in certain circumstances, not in every circumstance. But the point is that it would be possible for that to happen. That's how space and time works. It's very freaky, very weird, you know? What defines consciousness? To me, the consciousness means you're able to process information on a higher level, such that you're building an internal model and you're reacting to things not just through pure stimuli, but you're reacting to things internally because you are creating your own model of the world around you. That's consciousness to me. And humans do this. All other animals do this that we know of, except for perhaps shellfish, or certain marine animals. Plants do not do that. Plants do not process information in a higher level. They don't have neurons. They don't have a brain for that to happen. That's the medium in which we have consciousness, the brain. The brain is what allows for consciousness to occur. And if you don't have a brain, you would need some kind of neural network that can process that information that way. How come we've observed well-structured galaxies only 300 million years after the Big Bang? Yeah, good question. The answer is maybe we didn't. It could be the case that some of these galaxies we're observing aren't actually that young or aren't actually that old. They're actually a bit younger. It's just that the way we observe them through telescopes kind of distorts their size and distorts their shapes. But it also could very well be that, those are accurate. It's plausible that galaxy formation happened fairly early in the universe. It could be the case that the first stars emerged only 100 million years after the Big Bang. It's actually fairly quick. And then after you have enough stars, you're going to have galaxies eventually. And so, it's very possible that dark matter, which exceeds the amount of baryonic matter, the stuff we're made of in the universe, there's way more of dark matter than we. Dark matter would have seeded those early galaxies, right? In other words, dark matter clumps up and attracts our type of matter to attract stars, and it creates galaxies. That's why dark matter is integral for galaxy formation. So, yeah, it just might be dark matter that explains that. How much do we know about space percentage-wise? Less than 1%. How did humans develop consciousness? Well, our ancestors had consciousness way before we did. We just inherited it, right? We merely inherited consciousness. But animals going back all the way to the first fish were conscious. Fish are conscious to some degree. And so we know that consciousness evolved even in the oceans first. Why? Now, why would consciousness emerge in the oceans? Well, when the first marine animals existed about 500 million years ago, they began competing with each other. See, some of the first animals were not conscious. They were bottom feeders. They were just eating bacteria. However, over time, as these animals began competing, they had to develop a way of seeing others, seeing predators, escaping predators, right? That helped them survive. And so they had certain photoreceptor cells that evolved. The first eyes evolved. Okay, when you have an eye, you need a respective neural network to process that information. There you go. There's the beginnings of a brain. They didn't have brains that early, but the point is they probably had some early primitive form of a neural network which processed vision. Then, when the first land animals emerged, when Tiktaalik, for example, started to leave the waters for the land, their eyes had to see further. And so now they have to process more information because they're seeing further, right? Their field of vision is way more in the air versus the water. In the water, you can't, light tends to attenuate a certain way and you can't see very far in the water. It's like maybe 5 feet away from you. But in the air, you can see way further. And so our brains obviously had to get larger as we moved to land for various reasons, but one of them because we had to process more information. And so that's likely how consciousness evolved. Us having to survive, to fight off predators, to run from predators, to find food, just evolutionarily helped us to survive, you know? Yeah, I have a whole human evolution series. You can go check that out where I talk about how humans evolved. I briefly touch on our ancestors, but in the first video I touch on that. But is it possible that the universe sparked in a dark matter nebula? I don't know. How long until we're type 1? Well, given the current administration in America, I don't think we're ever going to reach type 1. No. So type 1 is a Kardashev scale degree of energy production for a civilization, right? So in other words, type 0 produces very little energy. We're essentially type 0.5 right now. We get most of our energy from burning coal and gas, fossil fuels, solar, wind, you know. But type 1 has like an order of magnitude higher of energy production than we, right? So they're producing as much energy as an entire planet, right? So they're producing a lot of energy. We're probably not going to get there for another at least century. But again, I think the Kardashev scale is a poor way of actually determining intelligence, or I think it's a bad way of categorizing civilizations. Because it's not just energy levels that are concerned. It's also, there's also other factors involved here, right? But we definitely are on the way to becoming a very globalized civilization, producing a lot of energy, and especially with the advent of AGI, perhaps ASI in the future. This will expedite the process. Anything's possible. Anything's possible. Thank you. Thanks for the kind comments. All right. Are you for nuclear power? Well, the problem with nuclear fission is that it's expensive relative to solar and wind. Solar and wind are the cheapest by far energy sources on the planet. Nuclear, at least fission, costs almost 10 times more than a counterpart solar facility, yielding the same net energy output. And so you might have a solar field producing 5 megawatts, a counterpart nuclear, perhaps it costs $2 million, but a counterpart nuclear facility yielding that same 5 megawatts costs maybe $50 million. And so nuclear does not make any economic sense. Although I'm not against it, and I'm not against it in principle. I think it's fine. It's just not economically viable if you want to scale energy at a level that will keep up with our demands. Like China right now, China is expanding heavily on their solar and wind power. In fact, China has more solar right now than America generates altogether in their energy for the year. In other words, China could power America if they wanted to. They could power the entire America with their solar. Right now, America only powers about 17% of their energy with solar and wind, but China has. I believe China has more of an energy demand than we do. I think, right? Yeah. China energy demand versus U.S. Yeah, China consumes about twice as much power as we do, and so they need way more. But the point is that solar and wind are obviously the clear winners in terms of scaling energy in a cost-effective manner. That's why nobody's doing nuclear in the Western world. Nobody's doing that because it's too expensive. Renewable energy is the future. It's the present. It's already happening. No, over lifetime, nuclear is not any. There's no reason to think that nuclear is better in the long term, either. Solar, you can have a solar plant last 30, sometimes even 40 years. You can have a solar plant last. That's way more cost effective than any kind of nuclear plant out there. By the way, nuclear fusion is a different story, though. I mean, nuclear fusion, that some companies are actually working on nuclear fusion right now. In fact, within 5 years, some of the first nuclear fusion reactors will be powered. Now, they won't be making massive amounts of power. They might be making as much as a fission plant or a gas plant. So they might start replacing many natural gas plants in the near future. Within our lifetime, we might have fusion power be a more dominant source. But solar and wind are not going to go anywhere. Those are very important to invest in as well. There's 70 reactors under construction, but there's far more solar plants under construction right now, especially in China. There's far more solar and wind happening. Guys, it's just so much easier to do solar and wind. So much faster, easier, and cheaper to do solar and wind. It makes no sense to do fission. Where are the extraterrestrials? Maybe we just have to listen better. Maybe civilizations exist in our galaxy. We just are not listening closely to them via radio waves. Maybe they are emitting their own state. Every time you send out radio signals from your phone or TV, those are being emitted out into space. And an alien civilization eavesdropping in on these signals may be able to deduce that intelligence exists on Earth. And so perhaps we are just not good enough yet at detecting other signals out there from other civilizations. The other answer is maybe they're just not enough of them. Maybe they're just too far away for us to know that they're, What is the answer to cooling data centers for AI? Well, just like everything else, when you invest in something and you invest in the research in it and development of it, you improve on it, right? 100 years ago, 80 years ago, the first electronic computers emerged. They were massive. They were hugely expensive and energy intensive. But now we have a million times, billions of times of more computing power in our pockets with a fraction of the energy. What does that tell you? Research and development will eventually make AI so energy efficient that you can power AGI with maybe one single large battery. Perhaps in the future that will be the case. The answer is solar, wind as well. We should be powering these facilities a lot on solar and wind. It's also not that much water. Like, a lot of people think that there's so much water being used for AI. Not necessarily. We use a lot more water for other things, namely animal agriculture, right? We use a lot of water to grow our crops, and those crops to feed the animals that we slaughter. And so, if you want to save water, the best thing you can do is to stop eating animal products, stop eating meat, if you want to save the most amount of water. Using ChatGPT is a fraction of that water that we use for eating meat. Is climate change reversible? Irreversible? Some of it is, yes. Some of it is irreversible. If we start, if we melt glaciers and sea ice significantly, that can't be restored. It would take thousands of years to get that back. So yes, in that sense, it's irreversible in that way. It's also irreversible in the sense that we're seeing species extinctions, right? We're seeing the acceleration of species extinctions. We can't get those animals back if they go extinct. Another problem is people's homes, people's livelihoods will be forever erased because of flooding, hurricanes, all these things. It's already happening. So that's irreversible. However, the good news is that we will adapt. We will largely adapt to climate change. And the good news is that CO2 levels are beginning to stagnate, and they will soon decrease. And so we are making an effort globally to do something here. Now, we could be doing far more and far faster, but we're doing something. So there is hope here. We have technology. We have other carbon capturing technology becoming advanced. Again, research and development. This is why science is incredibly important. This is why I preach about this. This is why science is my entire presence on TikTok, because the more we invest in research and great scientists and great thinkers, the better our lives will be. Science is the engine of our world. Science powers your phone. It powers this watch. Somebody had to engineer my clothing. Somebody had to engineer my shoes, my computer, my TV, my microwave, my car. Every time you turn the key in your car, there's 1,000 different processes occurring. Electronic modules, spark plugs, the right amount of heat, the right amount of energy, the right amount of fuel, the right amount of... That takes engineering. And everything we do requires... The road you drive on requires an engineer. The width of the road, the width of the asphalt, right? Everything we do around us, we're immersed in a world of science. And if you don't understand science, if we don't invest in science, if we reject science and the methods of science, if we say, oh no, let's get rid of these people on the science board, let's prevent this research because I don't like the word climate change, that's a problem. That is antithetical to a prosperous society which runs on science and technology. And so the answer is always knowledge, learn, invest in research and science. Every time we invest in science, we get massive return on investments. Massive returns. Why was the Earth different and changed the entropy at a certain time in the universe? I don't know what that means. Time is at 8:30. All right, a few more minutes, a few more questions. But I'm loving these questions today. Thank you guys for all the great questions. I hope you guys learned something and are inspired to do your own learning. Any book recommendations? Anything Carl Sagan. So here's one of my favorite books here, the Demon Haunted World. Cosmos. Anything Neil deGrasse Tyson for introductory science, or Sean Carroll or Brian Greene. Anything like that. Some of it is more advanced than others, but yeah, learn. Immerse yourself in learning. What is up with the science illiteracy lately? Yeah, it's look, we've embraced a culture. We've become complacent. We have taken for granted what we have accomplished culturally. In other words, the standards of science literacy have laxed over time because our culture does not care about science. We're so immersed in a world of science that we've essentially devalued it. We take things for granted. We take it for granted that we have a phone, right? We just want more and more and more and more. We want iPhone 18, iPhone 19, right? We're not happy with the iPhone 17. We want the iPhone 19. 50 years ago, anybody would have... That iPhone 17 is an incredible piece of technology, right? It's world-changing. And so we have kind of taken all this for granted. We've taken the fact that we have great scientists for granted, you know? So it's also the case that education in school is poor because many different reasons, but teachers are on a schedule. They have to do their curriculum. They're bounded by what their bosses say to do. The students are often don't have parents to talk to. They're at work. They're given an iPad, and all they know is an iPad and TikTok and social media. Their brains are focused on social media. They don't care about learning. There's a lot of factors involved, and so we need serious changes. And it starts with people talking more about science. It starts with people engaging more in the science world, in the STEM world. Learning more, or at least it doesn't mean become a scientist. I mean just learn more about the world around you. Learn more about evolution. Learn more about space and science and biology, and because it enhances the way you see the world. Science affects everything you do. Scientific thinking, because that's what science is. Science is a way of thinking. And it affects your way of finances. It affects your health. It affects everything. It affects your entire life. So it's incredibly important that we do that. That's why I'm here. Did you hear that Iran destroyed U.S. towers and climate dramatically changed in Iran? I don't know what that means. I don't know what a weird tower is. You're talking about HAARP. HAARP. There's no such thing as HAARP having any significant ability to change the climate. Now there's cloud seeding, right? People clearly can create mini clouds or enhance the rainfall from clouds by ejecting particles that are hydrophilic. But there's no such thing as modifying the climate to that degree. Yeah, HAARP doesn't even study that. That doesn't even have to do with weather or modification. It's just propaganda. It's a conspiracy. Dude said AI has a brain. No, I never said that. I don't think AI is conscious or has a brain. Do I think we're beginning, though, to mimic neural networks? Yes. AI is at the level in which we're building a mini neural network. It's not conscious yet. It's not quite conscious. It's not quite a brain, but it's the beginnings of an artificial intelligence. Oh, not me? Someone in the comments? Yeah. Did you hear about the fly brain they recreated? Yeah, I made a video about that. So a couple years ago, scientists took a tiny fly. Flies have very small brains. Their brains are maybe made of maybe a few thousand neurons. And the good thing about that is that we can take their brains and we can digitally image or scan. We can, first of all, they slice the brain in thousands of pieces. They literally microscopically slice the fly's brain into thousands of slices, and they digitally scanned each and every layer They scanned each layer of that brain, and then they plugged all the images into an AI system, and that AI system developed a 3D model of the brain and all the neural synapses and networks in the fly brain. And so we have mapped out every neuron, every synapse, every neural connection in the fly brain. And so what they did from this is they took this model and plugged in like a remote control to it, and they were able to make the fly do things in the model. They were able to make the fly eat or make the fly do this. And we literally took control of the fly's brain because we knew everything about the brain. And so yeah, that's a remarkable progress. Now, the next step is to do this in mice. Now, mice have far larger brains than flies, right? We're talking millions of neurons. And so it would be far more difficult to model their brains, right? Let alone a human brain. However, just imagine 20, 30 years from now, when we're able to do this to a human brain. Imagine being able to map out every neuron in our brains, every synapse, every connection. That will enable us to know exactly where every mental disease comes from. Alzheimer's, schizophrenia, anxiety, everything. We'll be able to map out every single thought. We know exactly where each and every thought you have comes from in your brain. And perhaps in the future, we'll have cures to many of these mental diseases that plague people today. That's the power of science. Why super AI isn't or has not discovered how to become conscious. I don't think, look, I think to be conscious, you have to be conscious like you have to have a biological brain. I don't know how you could be conscious in a computer. I don't know how a computer can be conscious. I'm not aware if that's possible. Now, if you hooked up an organoid, right, like a brain organoid, if you developed a brain organoid, which we're doing right now, but if you developed a brain organoid that had as many neurons as we do, then I think that we could create consciousness in the lab one day. I think we can. And if we hook that brain to an AI model, it's intelligent and conscious. It's pure. Imagine having that, right? Imagine replicating a human brain, and putting it into a robot. That's crazy. That's crazy. But I don't know if that's possible right now. I don't know if we're at that stage yet. We're probably decades away from that. Why do you think that only a flesh brain can get consciousness? Well, I'm not sure about that. I'm agnostic. I don't know. Maybe it's possible, but as far as I know, to experience the way we do, you need biochemistry. You need biological ingredients, right? Neurons, which exist in a particular environment, right? There's certain liquids and certain chemical ingredients and compounds, carbon-based compounds that make us experience the world. And so I don't know how that could be replicated mechanically. That's the thing I don't know how to do. It might not be possible. Is it true that light cannot escape a black hole? If the light travels past the event horizon, it's gone. It can't come back. However, black holes do emit radiation. And so it is the case that matter eventually comes out of the black hole. It just takes a long time. We're talking trillions and trillions and trillions of years. But black holes slowly evaporate away. They don't last forever. How accurate was Interstellar depicting a black hole? Very accurate. It was very accurate. It was actually one of the most accurate models of a black hole at the time. And the reason why is because they actually had scientists working on it. They had scientists were working on that film, literally, like really good theoretical physicists were working on that film. They had scientists there. They had like a lot of people working on that, so they made sure it was scientifically accurate. And the reason why that's a good question. You know, why is it that you see the black hole? Why does it have that weird shape? It looks like an umbrella, right? It looks like not an umbrella, sombrero, right? It has like, well, that's because in actuality, the black hole in actuality it's a disk. The black hole, the light around it, the event horizon was just a disk, right? However, the reason why it looks like this upwards is because the light is being bent. The gravity of the black hole is bending the light upwards such that when you're in front of it, you see the light being bent. That's why it looks so weird. In actuality, a black hole is just a spherical object with a disk around it, like Saturn, right? But gravity's bending the light. The gravity is so intense that light bends when you look at it from a certain direction, and that's why it looks like that weird shape. That's incredible. Did T-Rex have feathers? We're not certain, but it is looking like the case that baby T-Rexes had feathers, yes. And probably when they grew into an adult, they probably lost their feathers or their hair. They lost their hair. However, another dinosaurs is far more certain that they had feathers. We can actually see imprints of feathers in some fossils. We also see very similar features in their fossils to modern day birds. Yeah, we're certain that most other smaller dinosaurs had feathers. How can a black hole emit radiation when it has such great gravity? How does it escape? It's a quantum effect. Hawking radiation. I'm not a physicist, but I'm just explaining it as simply as I can. This might not be 100% clear, but quantum effects happen around the black hole, and so it creates two different particles, right? But one of them gets sucked back into the black hole. It gets trapped into the black hole's gravity, but sometimes the other particle remains, right? So you have this happening all the time. Over time, if enough of those particles remain outside the black hole, that's radiation. All right. My 8-year-old son asks, what makes the black hole? That's a great question. Black holes are just objects like any other object in the universe, like a planet. What makes a planet? Mass. Black holes are just massive objects, but they're so massive that, in other words, enough material, for example, like a star has. Stars are made of hydrogen, helium, carbon, nitrogen, right? That's what a star is made of. So that's what a black hole is made of. It's just that there's so much of that mass that light cannot escape from it, and so it's dark. Black holes are just dark. They're black. There's no light coming from it. And so that's why it's called a black hole. But there's nothing special about what it's made of. It's just mass. You just can't see it. You're gravitationally affected by it, but you can't see it with your eyes. Exactly, concentrated mass. In other words, it's so dense, right? Black holes are very dense compared to a planet or a star. A planet is, our Earth is fairly dense. It's made of iron, nickel. Our sun is even more dense because it's extremely massive. It has more gravity, right? So the things in it are more compacted. A black hole is even more gravity, so things are even more compacted, more dense. And that's all, That's all. So they're dark planets. Well, you can think of it that way, but they're not like, we don't really know what happens past the event horizon. We don't know if there's any, we don't know what it would be like to be down there. Because at that point, the thing about black holes, so what happens inside of them is that space and time itself, they're so massive that space and time itself tears apart. It becomes so twisted and manipulated that we don't even know how to mathematically figure out what happens down there. Time and space works differently down there in such a weird way that we can't understand it. So that's how massive they are. That's how dense they are. They physically alter space-time itself in a way that planets just don't do. So I wouldn't call it a planet. I would just call it a dark object. Sagittarius, center of Milky Way. How long is it? I think it's like a few thousand light years across. Let me verify. I was way off. No, it's about 32 million miles. So that's 32 million miles. That's a third of the distance from the sun. So think of the distance from here to Mercury. Or Venus. Mercury. Let's just say Mercury, right? That's how large the black hole is in the center of our galaxy. That's how big it is in diameter. From here to Mercury. And it has the mass of billions of stars. In that little area, it has the mass of billions of stars. Or millions of stars. A lot of stars. Just say that. Again, make sure you fact check me on the math. Don't just take my word for it. Again, I'm not here to be a teacher, by the way. I'm just here to be a catalyst for your discovery. I'm not here to be a teacher. I'm not a teacher. I'm not an encyclopedia. What was Sagittarius? A supernova? It could have been a large star. It could have been a very early large star that exploded. Or remember, the stars in the early universe were far more massive than they are today. In the modern day galaxy, they were on average 100 times bigger than our sun. We're talking massive stars, and so they were way more likely to go supernova and turn into a black hole. And that's probably how it began. You actually believe speed of light is instant. That would not be mathematically possible. So, although it's intuitive that when you turn on a light in your room, it seems instantaneous that you get the light. But that's actually not true. It actually takes time for light to reach your eyes. It takes about a second for light to reach your eye from the moon. From the sun, it takes about 8 minutes for the light to get to your eye from the sun. So if the sun suddenly died out tomorrow, it would take 8 minutes for us to know. But no, we can measurably detect that the speed of light is not instantaneous. It's a finite speed. Can we design self-replicating molecules in a lab? Not from scratch. We can't. In other words, we can't go into a laboratory and put some chemicals together and bam, you get a replicating molecule. However, we can catalyze the formation of certain RNA molecules. We have taken nucleotides, we've taken larger building blocks of DNA, and they have been catalyzed with rocks, minerals in rocks, clay phosphates in particular, and we've seen the spontaneous formation of RNA. However, that's not replication from scratch. That's just the polymerization of RNA. So no, we haven't been able to make life from scratch, but we're making the ingredients of life, and a lot of them we're making from scratch, and so. I'm not a scientist, but I do have scientific. I do have a scientific background, but I'm not a scientist. Why stars and planets formed differently? What do you mean? You mean how? Or why? So, our sun. Here, let me. I have some graphics here that might help you out. So this is how our sun began. This is called a solar nebula disk. And if you notice, it looks like like a disk. In the center of it is a lot of light, heat, energy. Why? Well, it turns out that when you have a gravitational center, things are attracted to it. Right? So you get more and more accretion in the center. And that's why the more mass you accumulate in the center, you get the beginning of stellar fusion, right? When you have enough mass together, you have atoms collide. Sometimes they collide and they create light. Energy comes off from that event when atoms smash each other. And so that's how stars get their fuel. Inside of stars are tons of atoms constantly moving so quickly that sometimes they collide and energy is given off in the form of light. So once that happens, there's still a disk around it, right? This is a baby star. During the star's adolescence, it emits a shock wave that pushes material outward. And so the stuff that gets pushed outward is colder, right? It's further away from the heat. And so it gets colder. And so that dust that was around it becomes fragments of ice and rocks. And those little fragments of ice and rocks become planets. And then those planets, by the way, in our early solar system, there were far more planets than there are today, but a lot of them got eaten away. Collisions. There was lots of collisions between planets, and a lot of planets also got eaten up by Jupiter. Jupiter was integral for our solar system formation. Jupiter likely absorbed many other smaller planets that no longer exist. And so over time, you have them become stable in their orbits around the sun. And that's why that's how our sun and planets evolved. The planets were formed very shortly after the sun formed. And by the way, I have a series about this on my TikTok channel, but Jupiter and Saturn were playing kind of like a tug of war. Their gravities interacted with each other such that some of them were actually tugged in closer to the sun, and then they moved away. They were in this dance where Jupiter actually came in closer. Actually, Jupiter came close near the asteroid belt. Jupiter almost passed Mars, and affected the way the asteroid belt formed, and so did it. Also affected Mars's formation. Mars could have been bigger, but Jupiter sucked a lot of that asteroid stuff from the asteroid belt and prevented Mars from getting bigger. So imagine if Mars were bigger, it probably would have had life by now. We probably still would be living. We probably have two twin planets, two twin Earths. But we may not have, because there would be more asteroids in the asteroid belt. It's, who knows, but interesting how the upper right picture looks like the human brain. So that's a good point you're raising. People often like to look at this picture and go, "Oh, look, it looks like a neuron. The cosmic web looks like a brain. Oh, maybe this is all a brain." But hold on a second. Wait a minute. First of all, this picture it's not a real, it's a render. It's not a real picture. Okay, we can't actually photograph this. And so we don't actually know what the cosmic web really looks like. And again, you have to be careful, because your brain wants to go pattern, recognizing patterns, pattern. We're good at that. We're very good at recognizing patterns, and so are you. But be careful. Not everything that seems like a pattern is actually real. Sometimes patterns are just, they don't actually correlate to reality, But yeah, that's a great insight, It's a great pattern recognition. How do scientists know that dark energy exists? Mathematically. So, Einstein thought that the universe was static, that it wasn't moving, it was just a static universe. And so when he was, however, he needed the cosmological constant to make that happen. In other words, there's something about the nature of the universe that wants to make it expand, but he said no, it shouldn't. He added the cosmological constant to make it such that it didn't expand. It didn't change or move. Einstein later realized that, oh my gosh, no, the cosmological constant is the thing that makes the universe expand. And so he was being a kind of chauvinistic about the universe's nature. And the cosmological constant, again, is a mathematical, it's part of the equation that tells us, yes, there's something about the space-time itself that makes it expand. Otherwise, you don't have expansion, but we can see the expansion. We know that the universe is, we can see the galaxies moving away from each other. We can see the redshifting of galaxies. So we know the universe is expanding, and that's what the cosmological constant is, or could be. There's other ideas. There's other mathematical ideas for what the dark energy could be, but it's probably got to do with the Einstein's equations. Okay. Could we create a magnetic field for Mars? Yes, we can. So this is a great question. Well, Mars doesn't have a magnetic field. How do we get it back? Well, right now Mars lost its magnetic field because it's just too small, right? Earth has enough mass to keep it hot in the center. When you have molten rock and molten metal, when that rotates a certain way around other material, you get a magnetic field. That's just basic electromagnetism. Mars doesn't have enough heat in its center for that to happen, and so it doesn't have a magnetic field. But wait a minute. All a magnetic field is just having electrons and charged particles moving around in a rotation. What rotates around Mars? Moons. Mars has 2 little moons around it, Phobos and Deimos. That is 2 moons perfectly rotating around Mars. And so wait a minute. If we could somehow create charged particles on the surface of the moons of Mars and have them emitted around the surface, around the orbit of Mars, wait a minute. We have a magnetic field, a torus, a plasma torus around Mars, protecting it from things like that, from harmful rays. So yes, that is one way. The one way we make a magnetic field on Mars is by generating charged particles from the moons of Phobos and Deimos. Another way to do it is harder, but we create a giant superconducting wire around the whole planet and we charge a lot of energy through it, a lot of charged particles through that, and we get a magnetic field that way, but that would be terrible for people on the surface. The point is that there are ways to do it. There are ways to do it if you're clever enough. Do you think Scotty will be able to beam me up? Does the moon actually exist? Yes. Gravity, Mike, how does it work? Einstein has relativity to explain that. We don't completely understand how gravity works, but we know it exists. You're asking great questions. How does gravity work? How does space work? They're great questions. But nobody actually knows the answer 100%. We're working on it. Again, if you want to know the answer, you could become a scientist if you want. These are big questions, though. Very difficult questions. So, but yeah, it's good. Roll on the floor laughing. NASA can't get a rocket outside the atmosphere. And you're thinking of Mars? Okay, there's nothing about the atmosphere that stops us from sending rockets through it. Rockets have gone through the atmosphere many times. We have satellites around the Earth. How does that happen? We have the International Space Station. You know, we have the Artemis people left the atmosphere, took pictures of the moon with their phones. Like, how can you possibly reject that data? You know, you're just like. To reject that, you have to reject all the evidence. You have to say, no, I don't care about that. Nothing matters. I'm right. You're wrong. You're all wrong. All they did is wrong. I'm right. Right? You have to be very lazy to do that. Dinosaurs were not the first species. No, dinosaurs are relatively new to the Earth. Life on Europa. Very well, maybe life on Europa. I think Europa has, there's evidence that Europa has water under its surface. There may be oceans under Europa. I think the best candidate for life is Mars and Enceladus. We know there's a very large ocean under Enceladus. And yeah, I have a nice picture of it here in my handy dandy book, Cosmos book. We have amazing nebulae to look at. This is Orion. These are large clouds that contain lots of stars. They're stellar nurseries. This is where stars go to be born. see here. Here's a baby star, a protostar. Star just beginning. Ooh, here's a beautiful planetary nebula. This was, so how this occurs, it's a very beautiful image. It looks like an eye, right? Well, the reason why it looks this shape is because there was once a large star in the center. And that star was roughly the size of our sun, likely, because this is a white dwarf. And so it was a mediocre sized star. And however, these types of stars, when they die, they don't explode. They don't have enough mass to explode. They shed away their gases, their plasma, because that's what stars are made of, plasma. And they slowly shed away those layers of plasma out into space. And those layers of plasma contain elements. And each color corresponds to an element. You know, blue, maybe oxygen, red, carbon, nitrogen. And so what happened is that slowly the star shedded its layers of gas away, hot, heated, superheated gas, in a spherical manner all around it. And that's why we see this nebula in this circular shape. This is how our sun will die. About 5 billion years from now. Incredible. Beautiful thing to see. And here's our sun, by the way. Isn't the sun an amazing thing? It powers all of everything we do. It powers us. It gives us life and energy. It's 93 million miles away. And you see tons of activity here. These are solar flares and magnetic storms on Mars. All right, so, here's a beautiful image of Saturn. Saturn's rings are very thin, but they're made of rocks and ice. Saturn also has a large magnetic field, larger than the Earth's. And so Saturn has significant auroras at its poles. You can see here and here. Beautiful planet. There's Venus. I don't believe it. I understand. It's overwhelming to learn all this and go, wow, this is real. It's overwhelming. But if you don't believe it, go learn it. Go test it. Go look at a telescope. It's all there to see. Anybody saying it's not real, means they haven't done the research, they haven't learned, they haven't taken the time to look at the night sky with a telescope. Another beautiful image of Saturn. Isn't that incredible? This is a real photo, by the way, taken by Cassini. So we've sent a cascade of probes to take a reconnaissance of our solar system. Probes like Voyager, have passed Jupiter, Saturn, Neptune. Cassini actually passed Saturn and its moons, like Enceladus. Here's one. Here's one of Saturn's moons, Dione, or Dione. I don't know how to pronounce it, but it's this tiny little ice ball. A lot of the moons of Saturn are little snowballs, literally made of snow. Look at them. Saturn has about 60 moons. 60 moons. Some of them are larger than our moon. Well, maybe one or two are larger. Most of them are smaller. Look at that beautiful image. This is yet another real photo of Saturn. This was taken by Cassini, and the sun's light, the sunlight was passing through the other side, and so this is an image of the sunlight passing through Saturn, passing through the Saturn's rings. That's just remarkable. You can see all the very different layers of Saturn's rings. Here's Uranus, another real image of Uranus. It also has rings. They're much smaller than Saturn's, but they still have rings. There's Neptune, Pluto. Here's the moon. Here's our moon. There's our moon. It's just another incredible rock. Literally just a rock orbiting around us. Isn't that just mind-boggling? And the moon is what keeps the tides happening on the earth. That's why we have tides. If you notice, if you live near a lake or live near the ocean or live near water, you notice that the level of water differs between days. Sometimes the day it's higher, sometimes it's maybe a few feet lower. That's because the moon is tugging on the water. The moon is tugging on the earth. And likewise tugging on the surface. Incredible stuff here. Oh, here's Apollo 17, the images from the Apollo missions. You can see the certain modules, the rovers. Oh, here's Phobos. This is one of the tiny moons of Mars. Now, Phobos is only 12 miles long. So it likely was just a captured asteroid. Mars likely just captured this asteroid over time. Here's Europa. And Europa has lots of these weird veins on it. Likely because of liquids on the near the surface. Cracks that are filled with water that froze. They froze over. They liquefied. They froze over. They melted. Just remarkable features. Here's Enceladus, a beautiful moon of Saturn. Look at that thing. This is Enceladus, a moon of Saturn. This is a real photo taken from Cassini from 2005. And you can see Enceladus has stripes on its surface, but they're blue. No, this is not real color. This is a mosaic in false color. But this is a real photo nonetheless of the surface of Enceladus, very close to it. And you can see stripes here, also because of water that is near the surface, which is ice. The surface of Enceladus is pure ice, either carbon dioxide or liquid water or water ice. But under the ice of Enceladus are oceans, liquid water oceans, right? We're talking miles deep of oceans, deeper than the Earth's oceans. And it's also salt water. And so this water can seep up near certain areas of the surface, not at the surface, but near the icy layer, and it goes into cracks and it melts and it freezes over and it melts and freezes over. And that's why Enceladus has those interesting, beautiful cracks and stripes on its surface. Enceladus also has these plumes. So something that Cassini did was extraordinarily find that Enceladus emits snow and vapor from its surface. There are literally these plumes, like kind of like volcanoes, that spew water vapor and snow from these plumes. And so that vapor goes into the atmosphere and causes snowfall on Enceladus. It's a winter wonderland there. It's almost constantly snowing. And also Cassini has looked into the plumes and they found water, carbon, and amino acids. Complex organics have been found on Enceladus. So we know that in the oceans of Enceladus are the building blocks for life. There may be life on Enceladus right now. We may be looking at a picture of aliens on Enceladus. They're just underground. They're just below the ice, living in the waters. That's amazing. And here's Titan, another moon of Saturn. This one is even more incredible because Titan has an atmosphere, much like the Earth. But it's very dense. In fact, it's actually denser than the Earth's atmosphere. Imagine that. A moon of Saturn has a denser atmosphere than the Earth. Now, it's not made of oxygen. There's no oxygen that you can breathe there. But it's made of methane and these hydrocarbons that we know also rains on the surface. We know that there's liquid lakes on Titan. On the surface, there's lakes of not water, methane. It's cold. It is so cold there that methane, which is usually a gas on Earth, it's actually a liquid here. It's so cold that methane's liquid. And so another remarkable way that life may exist. Perhaps life somehow is living on Titan, in the lakes of Titan. Who knows? In fact, we've landed on Titan. We've landed on the surface. And here we've sent a probe to the surface of Titan in 2005, and we've taken these pictures from the surface of Titan. Isn't that just remarkable that we can do that? Mind you, this moon is 700. We're talking millions of miles away from Earth. That's just remarkable. So, here's some galaxies. Spiral galaxies. There's all kinds of galaxies in the universe. Spiral galaxies, elliptical galaxies. Aren't they just beautiful? Just incredible. That nature itself can yield such amazing things. All you need is just gravity and some matter, and you get these amazing objects. Ooh, here's a galactic merging. Yeah, two galaxies merging together. Galaxy collisions have happened frequently in the universe's history. It's perhaps the case that our galaxy was the result of another galactic collision in the past. Just incredible. Here's a galactic group. You have, just like the Earth has a moon, so do galaxies have moon satellite galaxies orbiting around them. You can have a bigger galaxy with smaller galaxies orbiting around. And here is a remarkable picture from the Hubble Space Telescope. Now we're looking deep into the universe. We're looking billions of light years away. Now, if you notice something very strange in this picture, you see little streaks or lines That is not edited. That's a real. That's real. That actually exists. And those streaks is what we call gravitational lensing. And so, what you're seeing is dark matter or black holes, matter that we can't see with our eyes, but it's dark, but it has a gravitational effect. And so light is bending around those things, those objects. And so that's what we see when we look at we look through telescopes, we see the bending of the light, and that's why it looks like that weird streak. That's the evidence of dark matter. That's the evidence that black holes exist. That's the evidence that something's lurking in the universe. It's dark. You can't see it with light. Incredible. So, yeah. That's a taste of the cosmic perspective. So, all right. When do you think we'll be able to take high quality photos of exoplanets? Well, you need a big camera for that. To focus on such a tiny object so far away, you would need a gigantic lens. We're talking bigger than the Earth. and so that it's possible, but not practical. And so I don't think in our lifetimes we'll ever do that. But hey, you never know. The name of the book, this is a very old book. I got this when I was a kid. 20 years ago. This is when, when Cassini and Hubble were just bringing back photos. This called Cosmos, Images from Here to the Edge of the Universe, forward by Stephen Hawking. I don't think you can find this anywhere. I don't think they're available for purchase anywhere. Maybe on eBay. But yeah, I'm lucky I kept it all this time. Would it be possible to terraform Mars? Of course. Now, the question is, how long will it take? It depends on our technology. But yes, we clearly can terraform the surface. All you need to do is introduce some gases to make an atmosphere, heat up the surface. So there's lots of water on Mars. There's a lot of water on Mars. In fact, if you were to melt all the water on Mars, because it's ice, but if you were to melt it all, it would actually be enough water to create an ocean. We're talking hundreds of meters thick and deep. You can create a huge ocean just by melting the waters. But the problem is that you need a lot of energy to do that. How do you do that? And the only way we know of is to maybe shine very powerful laser beams on the surface. You melt the ice, you turn it into water, you get an atmosphere, you create gases from that, carbon dioxide gas. Right? You have to heat up the planet. That's the only logistics issue. How do you heat up the planet without destroying the surface in a way that makes it uninhabitable? Or perhaps some scientists have proposed sending bacteria to Mars. Perhaps if we were to infuse the Martian surface with bacteria that eat up percolates and certain elements in the soil of Mars, perhaps those bacteria can create oxygen, and that will inadvertently cause the heating of the atmosphere of the surface. There's a lot of ways to do it. We have a lot to learn about this too. Can we do an experiment and see what happens when we put MAGA inside a black hole? Can we ever realistically move planets like closer to the sun? Well, you could do anything. I can do anything in the universe, but You just need energy. You just need a lot of energy to do that, right? To move an object like a planet, you need lots of energy. Um, how do you do that? I don't work in NASA. No. I wish I did, though. I think NASA's awesome. So, all right, guys. I think I'm done. Thoughts on K2418b? They're saying it's the strongest biosignature. For an exoplanet, yes. Again, exoplanets, it's hard to really know if there's life on an exoplanet because we can't see the surface to the extent that we can see the surface of Mars or Enceladus or Titan. But yes, it's promising that the James Webb Telescope has new technology that allows it to see very deep into the atmosphere chemically, and there are certain compounds that we would expect to find in a planet with life on it, and we see them in other. We see some of this in other exoplanets, but we cannot confirm. We cannot verify. We have to go there to do that. Talk about Elon Musk putting plants on Mars. Given the trillions of stars, there has to be life out there somewhere. Yeah, absolutely. I think the mathematics just makes it inevitable. The moon is rusting. Well, the moon is not rusting in the way you think. It is the case that UV radiation can induce a kind of rusting chemistry on the moon. Because there's water on the surface of the moon. There's water. It's just frozen. And so when you have pockets of water introduced to certain radiation, you can get a kind of rusting. But it's not the same thing as, rust on a bicycle or, rust on the earth. It's a different amount of it. There's like barely any. We're talking molecular, right? We're not talking like when you think of something rusting, you're thinking of like the entire object getting darker. It's not happening on the moon. What will humanity do billions of years when the Earth gets engulfed by the sun? We won't be here. we may have the technology to move the Earth entirely. That would make way more sense than just giving it up, right? The Earth is a very amazing place. And to just say, oh, who cares? I think that's good. I think we'll be able to nudge it away from the sun, and eventually we may be able to create our own energy source, our own artificial sun, so we don't have to rely on our natural sun anymore. Or perhaps we'll be another system, star systems. Perhaps we'll be traveling interstellar distances. Who knows, we might find another planet beyond our solar system. Wait, imagine we can move our Earth to another galaxy. Yeah, remember SpongeBob? Just take the Earth and push it somewhere else. Okay. The Earth is so fine-tuned for life that any change to it in any aspect would deem it unfit for life. Any change at all? Really? So if I were to take one molecule away from the Earth, there'd be no more life? That's absurd. Clearly this is not the case. Clearly it's the case that although we exist within a certain parameter of conditions, these parameters are not somehow locked or, written in stone in the universe. That you can only have these parameters for life. No, clearly, habitable zones vary. You can have a planet that is vastly different in all those parameters, but still habitable for life, because the star it's orbiting is different, right? And so it's all relative. There's no set conditions that only life can exist within. It varies. There's nothing, in other words, there's nothing unique about our planet in the grand scheme of the universe. It seems like we're just another planet. It's amazing that we're here, I agree. But it doesn't mean that there's somebody tuning it for us. Thank you for gracefully guiding me away from hopeless nihilism. I appreciate you. Yeah, that's a great thing. That's a great point. A lot of people, they view science as, oh, it's just all a bunch of hopelessness, and who cares, and if there's no God, nothing matters. I see the opposite. I think that when you embrace nature, and that it just is the way it is, and there doesn't need to be a God, when you start embracing it, everything becomes more precious, right? Life becomes more precious when when it is just natural, because it's fragile, it's rare, it's finite. Yeah, here's like, I have up here the pale blue dot, and I guess I'll leave on this note here, because I got to eat, but here's the pale blue dot picture. This is a picture taken by Voyager in 1990, about 4 billion miles from the Earth. And that little dot, if you can barely see, is right there. That little tiny dot, that's the Earth. That's the Earth. That little dot from 4 billion miles away. And Carl Sagan once, the one who fought for this picture, he wrote something about this. He said, if you look at the Earth from space, you see a dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, economic doctrines, every hunter and forager, every hero and coward, every mother and child, every creator and destroyer of civilization, every king and peasant, every young couple in love, every helpful child, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in the sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those emperors and generals, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings. How eager they are to kill one another. How fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there's no hint that help will come from elsewhere to save us from ourselves. It's up to us. It's been said that astronomy is a humbling and character building experience. There's perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. Yeah. That's all we got is this one planet. You know, a lot of people today are so focused on looking down at our problems. Politics. Oh no, what Trump's doing. Oh no, what is it? We're all focused on the problems, but we often don't look at Earth from this perspective. It changes things. It changes your perspective about who you are, how amazing we are because of how small and fragile and delicate. Look how delicate that dot is. It reminds you of how important it is to live and take care of your life and take care of others around you. Because that's all we have is each other. That's it. We don't have another planet. We don't have a second Earth. All we have is this one planet. And so it places so much more importance on taking care of yourself, people around you, and the environment, and the earth, and animals. And the more you learn about the world, the more you embrace that, the more you appreciate things. When you understand life, when you understand biology, chemistry, and astronomy, and physics, you really appreciate the world. You really appreciate your existence. You really recognize the value in life. You know? So, yeah, people say, oh, without God, there's no purpose. I disagree completely. I think, sure, you can have purpose if you believe in God. That's fine. But I think it's a comparatively petty purpose. To just what? To be a sycophant for God. To follow his every command. To make sure that you get a good reward at the end. Sure, that might make you happy, but I think that compared to my perspective, where life is so much more precious and this life is so important. It's not about the afterlife, it's about the now life. That's all we know we have. I think that changes things. You know, I think if more people had this perspective, people would be more kind to each other. There wouldn't be as much war. I think if everybody understood this picture and understood the importance of it, I think that people would be way less violent. I think people would be way less eager to hate. So, yeah, that's it, guys. Hope you enjoyed. See you next time. And I gotta eat. Have a good week. Remember, your life is precious. All of our lives are precious. Not because of God, but because we just are. You exist. We exist. That's enough. All right. Good night.